Good morning, everyone. Welcome back with the second morning session of our school. It's a pleasure this morning to let speak of our next lecture, Veronica.
Thank you very much. Okay, so let me just start by recalling a little bit what we have seen yesterday. So the equation, the family of equations we are interested in are of this form. And let me just remind what P and Q and R are. So maybe we have that P is a polynomial and degree D of degree D and with a simple zero. Then for Q, similarly, also Q is a polynomial, but now of degree D minus 1. And let me denote by lambda. Lambda will be the set of 0 of P, so P lambda. Here, today, we have a new assumption, meaning that Q of lambda must be different from 0. And R is an holomorphic function. So R of, Z minus 1 as a convergent power series expansion. And this is convergent for Z bigger than some constant A. Okay, so that was the setup. And in fact, remember, we have this example, the equation square, which fit exactly in this family of equation. And why we are interested in this family of equation is because, in particular, they have an irregular singularity at infinity. Now, yesterday, let me just remind, this is somehow the overall idea and of this course. So we would like to solve equation with different method. Yesterday, we have seen the first one, so how to get a formal solution using the Poincaré method. And let me also remind how this solution looked like. Can you see if I write here? Okay, so the solution phi lambda has an exponential type behavior. Then there was possibly a square root or like some fractional power singularity here, and then a formal power series. And yesterday we have seen how these lambda and tau lambda were defined. So let me just remind here that lambda, I already said, is a 0 of P, and tau lambda was defined as Q of minus lambda divided P prime of minus lambda. Okay, this was the formal solution. And we have also seen that, in fact, it is Borel-Laplace summable. So we can go from the formal solution to the analytic solution using some Borel-Laplace summation. And this gives us what yesterday I was denoting by phi lambda A without the triddle. So this is analytic. Maybe just in a certain domain, and in fact, let me just write it's the Laplace transform, Laplace Borel of this phi tilde lambda A. Now, today, we will instead look at the Laplace method, so we will discuss the method C, and the goal is that we would like, again, to compute a solution in the, now starting from the position domain, but already analytic. And the goal for next lecture will be, in fact, to compare the solution that we compute here, which I will denote by phi lambda C, with the solution phi lambda A we have seen yesterday. Remember also that, as I was discussing at the end, we have seen that we can take the Borel-Laplace sum of a formal solution. A priori, it's not guaranteed that this is indeed also a solution of the equation. And what we will see, in fact, tomorrow is that yes, it is a solution of the equation because it corresponds to this solution phi lambda c. And the last thing I want to remark is that as a reference for today, I will focus mostly on this paper, which is on Archive and is a joint project with my collaborator, Aaron Feignes. I also mentioned this second reference because it just appeared on the Archive and is again another, is part of this collaboration with Aaron. And in the second reference here, you can find the discussion I was making yesterday about the Borel transform, the formalism of the Borel transform and Laplace transform, and some of the property that I discussed yesterday too. So yeah, since it just appeared, maybe you may want to take a look as well. Okay, maybe are there questions about what we have discussed yesterday, or? Okay, maybe I can just start. So what is this Laplace method? In fact, Laplace method is a kind of standard, and in particular, in engineer textbook, is one of the methods suggested to solve a differential equation. So what is it about? Essentially, you have to consider as an ansatz the Laplace transform. So you take the Laplace, you take as an ansatz the Laplace transform of phi, and then you solve for little phi. What does it mean? Here I'm doing, I'm on purpose, I'm not specifying, I'm not decorating the Laplace transform as I was doing yesterday. And this, in fact, will be somehow a crucial point in the way we have to decorate the Laplace transform, keeping in mind that we want to prove that something like that this true solution holds. The idea is you take phi, you plug it in the equation, and then you will get another equation for little phi, and this, and then you try to solve for little phi. But as I said, for us it's important to specify here which Laplace transform we have to take. So we have two labels. One is the coordinate, one is the starting point for the contour of integration. And so for us, we will use the coordinate zeta, and as a starting point, lambda. So now I will decorate everything with lambda, and this will be what I will denote by phi lambda c, so exactly that solution, and this will be little lambda. So let me just remind what this Laplace transform, how it was defined. So this is as a function of z, is defined as the integral from lambda to plus infinity of d zeta. And remember that zeta is the coordinate in the position domain, and z is what I usually call the coordinate in the frequency domain.
So here, it's a line.
I can also add the theta as we did yesterday, yes. Yeah. This lambda? No. This, yes, is just a root of our polynomial. I mean, in the example, in the square example, they are real. We have two roots. I don't know if someone has checked, but yes, in that case, they're real. A priori can be whatever. Okay, so this is the Laplace transform. In particular, as I was also mentioning yesterday, it's an integral transform. So what does it mean to solve for phi? We have to find a solution which is in the domain of the Laplace transform. The advantage of doing this is that, in fact, although we will solve an equation for phi, these give automatically also the well-defined solution capital phi which will be directly analytic in the frequency domain. So somehow here, instead of starting maybe in the most simple way with the formal solution, which is something that we can easily compute, and then try to understand whether the solution is Borel-Laplace summable and whether the Borel-Laplace sum is again a solution, we just start with a good ansatz in a sense. It's the one that will be already in a sense the Borel-Laplace transform of something. But we move so the difficulty in a sense in finding the solution phi. Okay. So let's see how does the equation look like for this type of ansatz once we plug in our equation. So like what will be the equation for little phi? I will do it. We have seen yesterday the property of the Laplace transform. So maybe let me just remind two of them. And in fact, okay. One was the property I, which tells us, now I will use the zeta lambda. Yesterday was just zeta 0, but you can extend it. So for, yes, the Laplace transform of zeta to the n times phi is minus dz to the n zeta lambda phi. And here n was a positive integer. And the other one is the third one, which is Laplace of zeta lambda of the fractional integral. Yesterday I denoted it with the lambda, but now I will use the minus k. Is zeta lambda of phi. So now here k here can be in 0 plus infinity. Okay, let me also remind how this operator was defined. So zeta minus k of phi is an integral transform. It's from lambda to zeta, and then you have the kernel of this operator is zeta minus t to the k minus 1 divided by gamma of k and f of t. I guess probably yesterday in the definition, here I didn't put the shift, but so that's in case it's not exactly equal, this is the good one. It might be a typo from yesterday. Okay, this is like just a quick reminder. Let's see now here. So let's use this property to compute the equation for phi lambda. Okay, so as I said, P is a polynomial. In particular, we have to do the following. So here we have our Laplace our ansatz is Laplace zeta lambda. We can put theta, but let me just drop it because it's an extra decoration that is not really important. So what does it mean? If I do p d zeta of this operation, so d zeta, p d zeta, what is it? It's just P0 plus P1 first derivative, P2 second derivative, and you go to PD this derivative. Okay, so in particular, you are going to use this operation. There is a minus sign that we can move to the other side. What you get is just a polynomial. You get the Laplace transform of a polynomial in minus zeta and of phi. So the first part, you will just get zeta lambda, and then you get exactly the same polynomial p, but now at minus zeta of phi lambda. Now here, q is again a polynomial. So the first part will be essentially the same. But now we have to use, so for the second one, we are going to use this property. So we know that 1 on z Laplace transform of something is this integral transform. And since k is 1, you see here that for k equal to 1, you don't have the kernel. So you just get an integral. So let me just... You get the integral from lambda to zeta, and then here, let me just put a t. And then you can imagine what you get for the other one. I erased the Fourier series expansion of R, but essentially it's the same. You use the property number 3. So what you get here is the Laplace transform, and then you have the sum from 0 to infinity of this Rj. You will have, now this gamma factor will contribute, and in fact you will get a gamma j plus 1 and a zeta minus t to the j. And then phi lambda of t. And of course an integral. Okay. I hope it's readable. So at the end of the day, we just write everything as Laplace transform zeta lambda of an operator, which I will call p at lambda of phi lambda. And what we should remember is that now, I mean, exactly how it is defined, this operator pi at lambda is in fact an integral operator. So once we have chosen as an ansatz a Laplace transform, we went from an ODE to an integral operator p at lambda. And in fact, we have a family of integral operator because we have one of them for each choice of lambda. So let me just write what is this pi at lambda. Pi at lambda is p of minus zeta plus the integral of q minus t. Sorry, we should just, let me just put phi everywhere. And then we have the rest, which is the sum. Okay. So in particular, what you see is that if phi lambda is a solution of this equation, then the Laplace transform is a solution of the ODE, of this ODE here. This is essentially what we have just computed. Notice also that here we had this 1 on z and 1 on z square. In fact, this shift in power of z reflects some property of this true integral operator, and in particular, this will be more singular than this other one. You see here we have some positive power of zeta minus t that a priori might compensate some singular behavior of phi lambda, and here we don't have them. So you just have we just have a polynomial, a function in t. Okay, and so as I was just saying, let me stress it one more, that, okay, so using this method, the Laplace method, we go from ODE to integral equation. And what is I mean, maybe integral equation doesn't look so nice, but in fact, if you are interested in proving regularity property, existence of solution, they might be nice. And in fact, I would say they are more regular. And this will be made precise also later. And the other feature is that in the case, so if Q of minus lambda divided by 3 prime of lambda, so what was denoted before by tau lambda, is rational, strictly rational, you can prove that in fact solving an ODE is equivalent, solving an integral equation in the position domain is equivalent to solve an ordinary differential equation. So let me just write it. I mean, the point is you can take derivative. So solving the integral equation for phi lambda is equivalent to solve the associated differential equation. Let me stress that the dependence is on zeta for is equivalent to solve an ordinary differential equation. What I mean is you really take derivative until the integral disappears. Okay, so here this is z, this is a zeta. And this, I mean, in the you can take a look. It's just integration by part morally, but let me just say, sorry, it's integration by part and the fact that if you have some fractional power, you don't have boundary terms. But if you want to see a proof, you can take a look at appendix B of the number 2, of the reference number 2 up there. You would like, sorry, Giordano, you were asking something? Okay. Okay. So the important point here is that, I mean, why this is useful if we can then take back the Laplace transform. So we have to be sure that we want to solve the integral equation, but and find a solution which is in the domain of the Laplace transform. And so what do we need? In fact, what are the property that we need? I guess I can erase this part. Let me introduce just the following space. I call HL infinity of sigma lambda the set of holomorphic function on omega alpha, sorry, omega, let me just put lowercase lambda, was norm is the sup on this set of the exponential minus lambda zeta, zeta minus sigma, and then f. So what is this? Let me just draw what omega lambda. So omega lambda is an open set. In particular, here we have our point lambda. We have to remove some sector and then and possibly also some other domain, some other region like this. So the domain will be a star-shaped domain where this point is missing as well. Maybe put across. So this is omega lambda in the complex plane. And here sigma and lambda are real. So what is this space saying? It's a space of a function which has a certain bounded norm. And this norm is given by controlling the behavior of the function at close to the singularity lambda. Sorry, in fact, here I should put a lambda. Sorry, zeta lambda is 0 at zeta equal to lambda, so it's just a coordinate. And okay, so we want to control the behavior of f at lambda, and the worst it can be has to be related to this sigma. So sigma controls the behavior of f close to this point, and the exponential controls the behavior of f when we go through infinity in some direction. So unfortunately, I have erased the definition of the Laplace transform, but if you look at the definition of the Laplace transform, remember, we will be integrating from lambda to infinity along a ray in a certain direction, and the measure is given by an exponential. So if we can bound this norm, in particular, for sigma greater than -1, so if we have an integrable singularity at the origin, this will be function in this space will be in particular function in the domain of the Laplace transform. So let me just make this remark somewhere. So in particular, if sigma is greater than -1, f in HL infinity sigma lambda, omega lambda, is in the domain of the Laplace transform. Of the Laplace transform beta lambda. Okay, so you might imagine that we are going to solve our equation, our integral equation in this space. But maybe before saying that, let me just mention a good property of the space, which is in fact the Banach space. So this is a proposition. So HL infinity sigma lambda is a Banach space. What does it mean is a Banach space? I mean, that Cauchy sequence, in fact, converge. But without going too much in the analysis, why do we care about Banach space? Because, again, a standard method to solve integral equation is to use the fixed point method, or the contraction mapping theorem, for Banach spaces. So if we define a space which is in particular Banach, and then we can prove that a certain operator is a contraction, we will get the existence and uniqueness of a solution of our equation.
I mean, you mean a function for which that's not this function.
Oh, sorry, yes. Yeah, thanks. Lambda is, okay, like for the definition is real, and then, to solve the equation, in fact, will be related with the radius of convergence of the series R, of R. Like, there was a constant A, which was the radius of convergence of this holomorphic function here. So for the theorem that I'm going to prove is that, in fact, this constant depends on lambda, on this rate of convergence.
And sorry, can you repeat the definition of omega lambda? So it's the part.
It's the color part.
So it's other area, these regions which are not taken into account.
Is because P lambda, sorry, the polynomial P has many roots. these are the other ones that I have to avoid. But these, I mean, this is just to give an idea of how this set is defined, and I think it will be clear in 1 second maybe why it has to look like that. Okay, so as I was just saying, Banach, we need this assumption because the idea is to use the contraction mapping theorem. For Banach space, which means in particular that if you have an operator T from a Banach space to itself, which is a contraction, meaning that the norm of Ty minus Tx is bounded by a constant and gamma is for 0, 1, then there exists a unique fixed point, x star, which means the following. I mean, there exists a unique, okay. This is the fixed point method, very quickly. Okay. And so what is the theorem I want to prove? And this is like the theorem 4 in the paper, in the reference, so it's theorem 4 in the reference 1, is that there exists a unique phi lambda solution of our equation p lambda equal to 0, and this phi lambda will be very of a special form. So in particular will be in the following space: zeta lambda tau lambda minus 1 plus HL infinity tau lambda. Okay. So what is this bullet means? This bullet, let me just write here, is the union. So, or let me just put sigma back. This is just the union over all lambda of this space. Because of, I didn't mention the other property of the space. There are continuous inclusion according to whether this sigma is bigger or smaller, as well as in terms of lambda. So you can take this. You really have to think that these two labels, sigma and lambda, tells you how much singular you can be at the point lambda, and how fast you can grow. You can grow at infinity. But okay, the point is the solution will be in some space of this form, and let me make another comment here. So why a solution in this of this form? So first, let me focus on this part, zeta lambda with this power, and look at what is still written here, this part here. In fact, both of them. Let's put them together. Remember that to go from here to what I will compare are these two, and in particular I have to take the Borel transform. So if you take the Borel transform with respect to the coordinate zeta of this couple, exponential z minus tau lambda, remember what we said yesterday, the exponential is a shift, so it gives you the coordinate zeta lambda, and the power is like the definition, again, get the shift. So what you get here is zeta lambda of tau lambda minus 1 divided by some gamma of tau lambda, tau lambda. So you will recognize that up to some factor, this behavior that that is there, it's related to this first part of the solution phi alpha. And what is the second guy here? Now, again, you have the definition. I erase it, but tau lambda is more regular than tau lambda minus 1, because in the norm of phi lambda, sigma lambda, remember that you have the sup, okay, you have the part in lambda, and then you have minus sigma. So in particular, if this function is tau lambda minus 1, it belongs to HL infinity tau lambda minus 1. But having tau lambda minus 1 means that your function f has to be more singular because of the minus 1, can be more singular. If you put tau lambda, then of course f cannot be as singular as this 1 because of the sign here, because of this bound that we have. So this is more regular than this part. And is the space, so it's written in this form because this is the space where we will in fact use the contraction mapping theorem. So it's more regular, and we are going to use the contraction mapping theorem here. So another part, yes, which is more regular. The message here is that the most singular part of phi lambda is of this form, as this behavior. And this will be useful, again, tomorrow to see that the relation between the two. Okay, so is the statement clear? And can I maybe just now write? Yes. Can I say a little bit more about the proof of the theorem, which I think I still have time. Okay, so I will erase again this part. So what we have to do now is, in fact, to write this operator in a much nicer formula. So so in particular, we want to write it in a form that we can recognize an operator which will be our contraction on a certain Banach space, which will be this one, and another part which will be related to this behavior. So okay. I think I can skip something because you have it somewhere in your note. So the first thing I'm doing is just isolating this part where you have P and keep the integral part to the right. So we have, this is a minus sign. And then we have the part in R. Okay, this should be exactly what you have. And now I'm going to divide by P. So in particular, I have phi lambda equal to the integral. And then I have minus Q divided by P of minus zeta. And same thing on the other side. Okay. So now it looks more or less of the form we want, to have a fixed point, to see it as a fixed point equation. Let me just denote this first part here as, so this V, the first part here is what I will call V0 lambda of phi lambda. And the other part here will be V0 star of phi lambda. So these are two different integral operators. They're also known as Volterra type operator. And I divide them in this way because this somehow is the most singular one, so it will be the one responsible for this behavior, and the other one will be part of the operator that give us the contraction. So in particular, okay, our equation look like this. The equation for phi now is this new, we can just rewrite it a bit more schematically this way. And now let me mention what are the properties of, so how will in fact we write this operator. So as I said, this is more singular. What does it mean is more singular? Is that first of all, we can find a solution phi lambda. We can find a solution phi lambda 0, which is a fixed point for this operator. So this is the first. And how does this solution look like? I mean, you have, in fact, you can write explicitly phi lambda in the following way. It's going to be p minus zeta, and then you have exponential some point b to zeta of q minus t divided by p of minus t dt. Okay, might be a little bit. I mean, you can also check that this, in fact, is a solution of of this operator. Here you are not using any contraction method, nothing. It's really just a computation that you can do. And written in this b is just a count of a constant, of an overall constant for this function. So it's just a point that you can pick inside your domain, and which does not have to be one of the singular points. So b is in omega lambda. This is the first thing, but what is the advantages of writing the solution in this way is that, in fact, you can prove that this phi lambda 0 belong to the space tau lambda minus 1. So is the more singular one. This is exactly the behavior that we want, and even more, in fact, you can really, if you use the expression of P and Q, you can see that the first, that the singular behavior is of this form, is a zeta lambda to this power. And that comes from the fact that tau lambda, which is not anymore there, remember how tau lambda was defined? Tau lambda was q of minus lambda divided by p prime of minus lambda. So here's, a bit roughly speaking, you see that you have q over p, and in fact, since p has a simple root at lambda, you can rewrite this part isolating the contribution that comes from lambda, which in particular will be of the order p prime of minus t, plus all the rest. And if you then integrate this part, you get the log, like a log contribution, and with the exponential gives you back the zeta tau lambda minus, the zeta tau lambda minus 1. But so this is the first part, and so in a sense, once you realize this, how you will construct your solution phi lambda, you will look for a solution which has two contributions. So the phi lambda 0 plus something else, which will be phi lambda star. And so what do we ask for phi lambda star? Now, if we just plug everything back, you see that you have a phi lambda 0 plus phi lambda star equal to, now V0 lambda is phi lambda 0 plus V0 lambda of phi lambda star, and plus, now same thing, V0 star of phi lambda, V0 star of phi lambda, sorry, the lambda star of phi lambda star. I hope it's readable. Okay, so in particular, the fixed point, now you have this new equation. This was no, okay, 0. So you are left with the 0 star of phi lambda plus these two together. Okay, V 0 lambda plus V lambda star of phi lambda star. Okay. So, oops. Now, this guy, so we know, oh sorry, this is a phi 0, phi 0 lambda. I think I'm, sorry. There was I mean, it should have been star from, it should be a lambda from the beginning. I don't know why I use it. Sorry, the idea is 0 is the regular part and star is all the rest. Sorry, this was a lambda star. And I hope now, so this is lambda, okay, in fact. Sorry. Now I hope it's consistent up to permutation of 0 and lambda. No, it's fine. Lambda star, okay. 0 lambda? No. Is 0 lambda again. Sorry, yes, is lambda star. I'm just using these ansatz and plugging it here. So I hope it's fine now. Okay, so this, now since we know that phi lambda 0 is of a certain form, we can actually check that this part, 0 star make no sense, this is lambda star, okay? Because this is this one, okay. Sorry, this is the, what's going on here? Sorry. These ones should be 0, in fact. I should have 2 0 and 2 star. Okay, now it seems correct. And here I'm using that V0 lambda of phi lambda 0 is, I mean, I can also plug it back. Okay, these two cancels because of the solution. Sorry, so this guy here is in HL infinity tau lambda. This is a bullet. So in particular, this is more regular. The operator lambda star, as I was just mentioning before, it's more regular, meaning that it maps something which is in tau lambda minus 1 and something which is in tau lambda. And therefore, what we in fact will prove, I mean, we proved in the paper, is that this operator here is a contraction on the space, on the more regular space, so tau lambda bullet. omega lambda. And in fact, if this is, I mean, the full operator that we have to check is a contraction is the sum of the two. But if this is a contraction, in fact, when you also the sum of the two is a contraction. This does not depend. Does not act. It's just a sort of constant term. It do not act of phi lambda star. So once we check this, we can use the contraction mapping theorem, and so claim that there exists a phi lambda so after checking all this detail, we can see that there exists a unique phi lambda star in the space HL infinity tau lambda of omega lambda. And in particular, the sum of the two is the solution we were looking for. Is in domain of the Laplace transform, and so our phi lambda C is well defined and in a certain sector, of course. Are there questions about this part? So maybe let me just stress what unique, I mean, here where I'm saying uniqueness, this uniqueness is always up to, I mean, once you fix certain normalization, because we are solving equation, homogeneous equation in a certain sense. And here the choice of the normalization is in this choice of the starting point here for the solution phi lambda. This is one thing. The second remark I would like to make is that having the so using this fixed point method give us the uniqueness, and this will be also a crucial point in the proof, like to show that this is proportional to the phi A of lambda. So we will really use the uniqueness and the fact that we have this good candidate on one hand to compare with. I have already this. There is another important aspect that, I mean, it seems that solving integral equation, it's kind of a bit more, give us an existence, a uniqueness result, but like if I really want to get the solution, how do I compute it? In fact, it is also, I mean, there is also an algorithm that a priori one can try to implement to solve, to get an explicit solution. And once you have this, the idea is you just plug in the first ansatz. So maybe let me just start. Let me just write more generally. If you want to solve something like this, you can build a sequence. So you can define Cn as T of x minus 1, and you start with you take a starting point at 0, and then you go iteratively like this. So you can build your solution x star as, in fact, this procedure at some point would stop. So you can do it iteratively in this way. And I think it would be nice maybe to see whether this work, I mean, like, or to try to compute it in the example square of yesterday. So maybe let me just conclude with, I haven't tried myself to do it in this way, but maybe let me just leave it as a final exercise. So just for our example, square, you can try first of all to compute to this operator. So I'm saying 1 and minus 1 because these are the two roots of the polynomial which appear in the equation star. And you can try to solve like the integral equation. For instance, doing it numerically in this way. Or you can also try to take the differential equation associated to this p hat. So go back to ODE still in the position domain. Here you will have in fact plus minus 1. Go back here and again and solve the ODE. So in both ways you will get a solution. So the idea is to compute phi plus minus 1 in both cases. And in particular, if you do this, I think it will be also interesting to, so maybe here as a second exercise, it will be interesting also to see which type of differential equation you get. So let me just write which type of ODE in this position domain you get. And by type of ODE, again, I mean, as we said yesterday, whether it's regular or irregular, if you want also the rank, but maybe most important here, but which type is really, can you say if it's regular, irregular at zeta equal to plus minus, or like at zeta plus minus 1 equal to 0. In this way, you will also get an idea of how these, how integral equations are in a sense more regular, or even though if we turn them back into an ODE, they will be more regular than the differential equation you started with. And yeah, I guess maybe I can stop here if there are questions.
Why is zeta sum?
Ah, sorry. It's this coordinate. You mean this one?
Yeah.
It's just a translation. Yeah. It's what is responsible when we take the Borel of the exponential.
So the integral equation you had when we tried to solve it like knowledge, well, you kind of expansion of this.
I mean, yes, you can take as an ansatz a formal power series and then integrate term by term. That's an option, yes. But I mean, integrate term by term then in T. So since we have terms that look like this, okay, like the first one was Q minus T, and then you have phi lambda T. So if you take now phi lambda T as some series in T to the n, then you can try to integrate term by term. And I mean, the point is you can do it formally and then ask a posteriori, did I get something convergent or not? In fact, remember, sorry. Yes, it depends even if you look at the equation written this way or when you divide by p minus lambda. But okay, I mean, this maybe doesn't really affect much. So yeah, I think you can also try to solve it. And maybe, let me think. I don't know how much this will be equivalent to do this iteration method for the other, like once you do the integral equation approach. It might be, you might get this. I didn't try myself, so you might get the same thing.
Okay, any other questions?